And I said, no, it's not the same problem we did last time. The problem we did last time looked like this. T-test for independent groups. What do we see? Independent groups, right? We've got one group that's in the experimental condition. That's Ann, Boris, Clyde, Dana, Eric, and Fiona. And we've got another group that's in the control condition. That's George, Harry, Ivana, Justin, Kelly, and Lauren. Right? Two independent groups, each one experiencing one level of the independent variable. Right? Separate kids, separate experiences. Today, we're going to look at that same design and concept, except now we're just talking about George, Harry, Justin, Kelly, or Ivana, Justin, Kelly, and Lauren. Okay? So now we've only got one group, and that group is going to read a story in which none of the characters has the same name as any of the readers, and then they're going to read a story of comparable complexity and length in which each reader's name is substituted for a character's name. So now we've got same group of kids getting tested on two different books. So when we did independent groups, we were doing a between subjects design. Now we're doing related groups, right? Because the kids who read the experimental story are related to the kids who read the ordinary story by virtue of being the same kids, right? So now we have dependent groups or related groups, and we can explore the same question. Will reading a story with your name in it make you read for a longer period of time than reading a story that doesn't have your name in it? But now we can make a comparison within subjects, meaning every child will read both stories. And we can do things like counterbalance the stories, so half the children read the modified story first and half of them read the ordinary story first. It's not a problem. Easy to do. As long as all the kids read both stories, we're in good shape. Okay? But because it's the same kid in both conditions now, we do a slightly different test. Slightly different test. The related groups t-test is very similar to the one we did before. If you look at this chart from last time. We did the t-test for two independent samples last time. This was the formula we were shooting for t-observed. We did things like calculate the estimated pooled standard error, remember that? And we did different things like calculate pooled sample variance, and sum of squares pooled, and degrees of freedom pooled, things like that, because we had two samples of kids. Now we don't have two samples of kids. We don't need to pool anything. What we're really interested in now is the difference between the kids when they were reading the story in the experimental group and when they were reading the story in the ordinary group. So, same kids, two stories. But because all the things like individual differences are held constant across the two conditions, rather than pooling now, we're going to focus on just the difference in the student's performance. So, our formula for t-observed is now the mean of the different scores over the estimated standard error of the different scores. And if you look at the formulas we're going to be using, they look pretty similar to the ones up there, except now instead of adding two scores together, instead of having two scores added in little subscript P's or 1s and 2s everywhere, you see subscript capital D. And that tells you that we're looking at different scores. This is a visual clue for you to help you know which kind of test you should be doing. Because on the test, I'll ask you. I'm not going to say, oh, do a related groups t-test. I'll say perform the appropriate t-test. And then if you look down, it says like calculate the sample variance of the difference. You'll see something like this or like this. And if you know what the symbols mean, it will give you a hint which one you're supposed to be doing. So the notations will give you clues about what calculations you should be doing, but I'm not going to tell you because I expect you to know what the notations mean. All right? So you'll see the formulas are very similar. It's important when you prepare your note card for the test that you write out both sets of formulas and mark everything clearly so that you can tell the difference. If you do the wrong t-test, because when we take the test for this unit, half the students in the class will get problems that require them to calculate a full independent groups t-test, and the other half will get problems that require them to calculate a full related groups t-test. And you don't know which one you're going to have to do. Okay? You're going to be asked questions about both kinds of tests, but you only end up having to calculate the full thing for one, because it takes a while. And I want you to have time to go over your work, because this is our first full statistics test. Okay? So you don't know which one you're going to get, so you have to be prepared to do either one. And it's just going to depend on where you sit. Okay, so and which test I decide to randomly give you. So you won't know. Okay, so these are our formulas for today. So you want to pull that sheet out, have hold of that. Let's go ahead and talk about this t-test for related groups now. Okay, so now we've got one group of kids, and you can see that our data is set up a little bit differently. Because now, with just one group of kids, I actually have 2 scores for each child. I have a score from when they read the modified story, and a score from when they read the ordinary story. Okay, see that? Now, if you happen to look back at the handout from before, you'll notice I've used the exact same numbers. Okay. So any differences we observe here are going to be differences in the kind of test we do. The math, in many cases, is going to look exactly the same. So we have, you can see here, average for the modified group, 10.33, just like it was last time, right? Hasn't changed, same numbers, should be the same average. And then the average for the ordinary group is 6, just like before. Now, what's different here is that I have calculated a new column of data, which is the mean of the difference scores, okay? And that's written as the capital M for mean with the subscript big D for the difference scores. So all I did was calculate the difference between the two conditions. So I did modified minus ordinary, modified minus ordinary, modified minus ordinary, okay? I did that. That's where those difference scores came from. Those difference scores are the scores we do this t-test on. Okay? We don't pay any attention after we calculate those difference scores to the raw data from the individual conditions. We don't care anymore. We've calculated the difference scores, and that's what we're going to do our math on. So in this regard, the t-test for related groups looks an awful lot like the t-test for single sample. Because what we've done is calculated difference scores, and now we're just going to do all our math on this one set of scores. Okay. Now, if I do the math here, I get an average for this group of difference scores of 4.33. That shouldn't surprise anyone. Okay, 4.33 is the average for the difference scores. Makes sense? It's also the difference between the averages for the others, for the sets of scores, right? But that's my mean difference. If you take a look at the formula sheet, okay? If you take a look at this formula sheet, you'll see that the numerator for our t observed is that mean of the difference scores. So as soon as you have that data, you know what the numerator for that formula is. You're done. It's really fast. All right. So we've got that. And ultimately, you can guess, just like we had to do sum of squares before. We have to do sum of squares again, but now we're going to do sum of squares for the difference scores. So you can see that I did the sum of squares for you, because you guys all showed me you could do it last time, so we're not going to spend time in class doing it again, because I'm not a fan of busy work. I don't think you are either. There's enough stuff to do in this class without doing stuff that you don't need to do. Okay? So all I did was calculate the deviations for each child. Notice that when I added it up, I got 0.02. That's okay. That's that rounding error thing we talked about, right? So it's pretty close to 0, so I'm pretty confident I did it right. And then I square all those deviations, and I get a sum of squares here, and this is the sum of squares for the difference scores. So SS sub big D. So that's where that number comes from. You guys should be able to go ahead, you should be able to do that just like we did it last time in class if I give you that to do on a test. Okay? It's exactly the same procedure we used last time. All right? Does anybody have any questions about any of those numbers up there before we proceed with the problem? Everybody knows where everything came from? Okay. All right. So, now we move down here. So, as usual, first thing, we need the null hypothesis and the alternate hypothesis. And we remember that we have to have 5 things, right? When we state our hypothesis, we have to be clear what groups we're comparing, what we're comparing about the groups, whether we're talking about a significant difference or not. If we're talking about a significant difference, the direction of the effect. And it needs to be clear in our description whether we're talking about a between subject comparison or a within subject comparison. Those are our 5 things that are, when we describe a study, we have to make sure we do. And that's true in a hypothesis or in a summary of the results. So, what groups are we comparing here?
The modified and ordinary stories, or
Those are the stimuli, yes.
whether reading a story with your name,
What?
or versus reading a story without your name, will cause you to read for a longer period of time.
Okay, so we're comparing children who are reading, we're comparing the reading time of children who read 2 stories. One of the stories has the child's name in it, the other story doesn't have the child's name in it. We're comparing the reading time, right? That's the dependent variable. With the null hypothesis, are we predicting a difference? No. So we predict no difference in how long children read, whether they read a story that has their name in it or a story that doesn't have their name in it. Right? Now if I say that to you again, does that sound like a within subject design or a between subjects design? I predict no difference in how long children read, whether they read a story that has their name in it or if they read a story that doesn't have their name in it. It should sound like within, because this is a within subjects design, right? We want to be very clear. It should be clear from the description how what we're comparing here is different than what we compared last time. If you need to say it in multiple sentences to be clear, do so. In this study, we are testing a hypothesis using one group. Children in that group will read a story with their name in it and a story without their name in it. The null hypothesis is that there will be no difference in how long they read either story. If that's what it takes for you to be clear, 3 sentences is fine. What I care about is clarity, not about brevity. I need it to be obvious from your description that you know all the relevant information. Okay? You'll get better at being briefer the more you do it. All right, so that's our null hypothesis. What's our alternative hypothesis? Yes. Okay. Children who read a story with their name in it will read longer than if they read a story without their name in it. Great. Sounds like a within subjects design to me. And we've got what groups we're comparing, what we're comparing about the groups, that we're predicting a significant difference, and the direction of the effect. It would be even better if we said children who read a story with their name in it will read for a significantly longer period of time than children who read a story, or than if they read a story without their name in it. Yeah. And we've got all the things. All right. So not super different from what we did last time. The important distinctions are in being clear about what you're comparing. And that in this case, you're talking about comparing one group of kids' performance to themselves, as opposed to the performance of two separate groups of children. That's important. So next it says, are you going to use a one-tailed test or a two-tailed test? One-tailed test. Why would it have changed? Has the alternate hypothesis changed fundamentally? Isn't it still a directional question? That's what dictates whether it's a one-tailed test or a two-tailed test. Whether it's within subjects or between subjects doesn't matter at all, right? The only thing that guides whether you do a one-tailed test or a two-tailed test is the directional nature of that alternative hypothesis. If that alternative hypothesis is directional, it predicts a particular pattern of results, that one group will be faster or slower or longer or stronger or whatever than the other group, then you're doing a one-tailed test. If it just says that the groups will be different somehow, but we don't know how, we just think somehow, then it's a two-tailed test. It doesn't make any difference whether you're talking about a between subjects or within subjects design. So we're still doing a one-tailed test. Still. And it says, given an alpha level of 0.05, what t-score will define the boundary of the critical regions for a hypothesis test? In other words, what's the value of t critical? What do you need to look up this value? Well, we know from last time. What are the three things we need to know to look up the critical value for t? We need to know degrees of freedom, alpha, and whether it's a one-tailed test or a two-tailed test. Now, this is not really something you need to put on your card because you're going to get this page when you take the test, right? And you're looking at this chart, and what does the chart tell you have to have? Degrees of freedom, whether it's a one-tailed test or a two-tailed test, and alpha. So as long as you know that these proportions here mean alpha levels, you're golden. But we know that we're doing a one-tailed test, right? Because it's a directional alternative hypothesis. One-tailed test. We know that our alpha is 0.05, so we know we're still looking in this same column. Right? Because this is the one-tailed test with alpha 0.05, so we're still looking here in this middle column. What we don't know yet is what degrees of freedom we should use. Now last time we did degrees of freedom pooled, which was degrees of freedom for group 1 plus degrees of freedom of group 2. But this time we've only got one group. So if you had to be, brave, and you had to guess what degrees of freedom we might use, knowing that it's entirely fine if you're wrong, but it will be super incredibly double awesome if you're right. What degrees of freedom do you think we would use? Yes?
N-1.
Hmm?
Is it
N-1. In fact, what it's going to be is, we're going to calculate degrees of freedom of the different scores, which is the sample size of the different scores minus 1. And how many scores do we have in the different scores? 6. It's like magic.
Too much magic.
Minus 1. Huh? I know! I've had students go, and I'm like, it's 6 minus 1. I believe in you. All right, so that's where that's coming from. We're using the different scores. That's our sample, right? I told you that's the set we care about. So that's why it's N sub D. It's the number of scores in the difference set. Okay, 6 scores. And that's the degrees of freedom we're going to use. So now we know we're going to use degrees of freedom of the difference because for the related groups test, everything is sub D. Everything. Sub big D everywhere. So now we're going to go down here to 5 and cut across. What do we get? It's hard to do that over my shoulder, get the angle wrong. Okay, so it looks like it's 2.015, is that right? Is that the right one? Okay, now we always round to 2 decimal places. So what's our critical value?
2.02.
2.02. Okay, so first we saw that T critical was 2.015 because we always round to 2 decimal places. That's going to be 2.02. And what's the other thing we always do?
Positive.
We're going to mark the polarity. That's right. This is a one-tailed test, and we're looking at the positive tail because we're predicting that the kids are going to read longer when they read the modified story than they read the ordinary story. So positive. Okay? Everybody still with me? Now, I'd just like you to know, just for fun, because, you know, it's a nerdy, fun math thing, that if we compare, so today our degrees of freedom is today our critical value is 2.02. Last time our critical value was 1.81. Our critical value has moved further out in the tail when we do it within subjects design. That's making it harder to hit the critical region, right? Because it's moving further out in the tail, right? It's getting further and further out. That's making the critical region the skinnier and skinnier and skinnier part of that tail. Does that make sense? Within subjects designs, because there are no individual differences between the groups, we make it harder to hit the critical region. We basically up the difficulty so that we don't commit a type 1 error. So we make it harder by changing where the critical value is. That's why we use different degrees of freedom. Okay. So, everything else being the same, if you do a study between subjects and compared to within subjects, the critical region, the critical value will always be further out in the tail for within subjects design. Okay. So, we figured that out. Now we have to calculate the following for the difference data. Right? Well, we already did A, right? Degrees of freedom of the difference. That was 6 minus 1, 5. Feeling the power of our college education right there. Okay, and then next is the sample variance of the difference. All right, people, we're going to live on the wild side now. What did we discuss yesterday about how to calculate sample variance? What did I say about sample variance? Sample variance is what? Sum of squares over degrees of freedom. Yep. And now, I told you, memorize that formula, right? Live it, breathe it, tattoo it on the inside of your eyelids because it's never going away. Well, guess what? How do you think we're going to modify this formula for this t-test? We're going to put a D on it. Yep, look at us. We're crazy. All right, we're going to put D's on there. I know. Living the wildlife. See right there. Go wild. Put D's on stuff. Okay, so you know where that sum of squares of the difference is, right? I showed you before. Quit having fun. This is math. We're all supposed to be miserable. She's smiling. I love it. She's like, this is actually fun. It doesn't suck. All right. Isn't it nice when math doesn't suck? Math should be fun. Math is great. All right, so we know where the sum of squares of the difference is, right? We did that before. It's up there at the top of the sheet. That was 81.34, right? I gave you that already. Because I was being nice. Okay, and now the degrees of freedom of the difference we figured out already, right? That was 5. So what is our sample variance of the difference? You don't have to do that in your head. But you do have to use a calculator. 16.27, I have votes. I'm looking around the room, thumbs up, okay? All right. So there's our sample variance, okay? Now it says we have to calculate the estimated standard error, okay? Estimated standard error. All right, last time we had this big fancy pants formula with like square roots. Okay, last time we had something that had like the square root, and then it was like sample variance over the sample size 1, and sample variance over sample size 2, and all this stuff. We only have one sample this time. So we're going to do estimated standard error of the difference, sometimes referred to by my students as SMUD. SMD, SMUD. And we can do this one of two ways, but the easiest way to do it, got that square root thing in there again, because that's how we get estimated standard error. Here's what we're going to do. We're going to take the sample variance of the difference, and we're going to put it over the sample size of the difference. You could almost predict that from what we did last time. In fact, you totally can predict it, because the formulas are all related. Alright, so now I know I need to do the square root of 16.27 over the sample size of the difference, which is 6, not 5. Don't use degrees of freedom. And what is 16.27 divided by 6?
2.71.
I have a vote for 2.71.
I concur.
You concur. All right. One time I was teaching this class, and I had a guy who just started shouting out numbers, and people were like, yeah, that's right. And it turned out he was just making them up. And people were like, it doesn't make any sense. And I'm like, well, he's the only one who's been saying anything. Everyone else has been going, uh-huh. And I'm like, so, you know, garbage in, garbage out people, he's not doing anything. And he's just like, I just wanted to see if everyone would say yes. And they did. And so we had to go back and do the whole problem again. And I've done this problem over and over, so I was like, that's not the right answer, but okay. Everyone's going, yeah, that's it. And I'm like, do your math. It won't kill you. It's not like it's that hard. All right. We're doing square root of 2.71. 1.65.
I agree.
You agree. See, it's a form of moral support. We're a team. All right, so our estimated standard error is 1.65. All right, well, guess what? What was our target formula? Our target formula for T observed was the mean of the difference scores over the estimated standard error of the difference scores. That was our target formula, right? Okay. Well, we saw at the beginning, right up at the top of the sheet, that the mean of the difference scores was 4.33, right? And now our estimated standard error of the difference scores, 1.65. So what is T observed? 2.62. Okay, just 2.62? Positive 2.62. We're going to get in a habit. All right, so we're looking up in the positive tail, so we're going to evaluate the null hypothesis. We're going to put the critical value here. And the observed value here. Okay, our critical value we said was what? 2.02 positive. And this is 2.62 positive. So that one's bigger. When it goes like that, it means
Reject the null.
reject the null hypothesis. We have a significant difference. Okay, is everybody with me so far? Everybody knows where every number came from?
Yes.
Why we did what we did? Yes.
So you reject the null because the observed value is bigger than.
That's right. The observed value is further out in the tail. So the probability of getting this value, the critical value, is 0.05. That's our alpha. The probability of getting this is less than 0.05. And that means we have a significant difference. There's a smaller chance of getting this number, the observed value, than we would expect by chance, if we're willing to take a 5% risk. So we think, well, the fact that we got this particular number means probably our manipulation did something important. All right, so we have now evaluated the null hypothesis. Now we're going to calculate effect size. We're going to do the same thing we did last time, Cohen's d and r squared both. Cohen's d for the related groups t-test. Remember last time we talked about how Cohen's d is always a mean difference of something over some standard deviation of something, right? That's always, Cohen's d is always a mean difference over a standard deviation. So, what mean difference do we have to work with? The mean of the difference scores. It's almost like it's right there. Same numerator as the t-test. Cohen's d always uses the same numerator as the t-test. All right, now we need a standard deviation. What standard deviation might we use?
A1.
The standard deviation of the difference scores. It's, oh my gosh, it's almost like there's a pattern. So then the question is, how do I get the standard deviation of the difference scores? Because I haven't calculated that yet. Well, the standard deviation of the difference is going to be the same thing as what? The square root of the sample variance of the difference scores. Because standard deviation is the square root of the variance. Ah, 3510. You did actually teach me something useful. Okay, so if I know that I need to take the square root of the sample variance of the difference scores. What was our sample variance of the difference again? 16.27. Okay, and what's the square root of 16.27? 4.03. Okay, so my mean difference was 4.33. My standard deviation of the difference scores is 4.03. So what is my Cohen's d? 1.07 I have a vote for. Yes? All right. I got the thumbs up guys in the back. They're like, yes! Yeah. Whoa! All right. 1.07. All right. And given what we know about Cohen's d, is that a small, medium, or large effect? Large. Very large. Very large effect. And not surprising, we got a statistically significant result with a sample size of 6. We would expect that effect to be really big. For us to observe it with only 6 kids, it's got to be a huge effect. It's got to really matter to kids that their name is in the story, or we wouldn't see it. Because our sample is tiny, 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 6 kids. So basically all the kids thought this was really good, or most of the kids thought it was really important. One kid didn't care, but it's free. There's always some kid that doesn't care. Okay, so that was Cohen's d. Everybody good with where all those numbers came from? All right. Now r squared. Remember, r squared has as its basic formula t squared over t squared plus degrees of freedom. 2 rules about r squared. First rule is the t is always, which t? Observed. That's right. So that's t observed. So our t observed this time was 2.62. 2.62. All right. 2.62 squared plus 2.62 squared plus some degrees of freedom. And it's always which degrees of freedom? The one you use to look up the critical value. always the one you use to look up the critical value. So in this case, it's 5 degrees of freedom of the difference, right? Okay, so this one's going to be 5. So what's 2.62 squared? 6.86. Waiting for some thumbs up? Okay. 6, take it.
6.86.
6.86. Okay, and what's 6.86 divided by 11.86? 0.58. Or 58%. That, if for R squared, is that a small, medium, or large effect? Enormous. Enormous effect. That's huge. It means more than half of the variance between these conditions can be explained by the manipulation. That's enormous. Okay, so this is also a very large effect. All right, rock on. Now, here we are down at number 7. It says, summarize your results in one or more complete sentences, including an APA-style statistical statement. Okay, so I'm going to give you a minute to try and do that. Remember, you have to include everything that we talked about before. So your description has to include what groups are being compared, what was compared about them, the direction of the result, if it was statistically significant, and the description needs to make it clear whether it was a between subjects or within subjects comparison. We also have to have the APA-style statistical statement. So while I pull up the class website, you guys figure out what that's going to be, and we'll check it. Over something exactly how it was covered in class. Lecture videos. Lecture videos are awesome. I agree. Has anybody watched any of the lecture videos? Do they help? It's nice having those videos. Thank you, Javier and Kristen, for doing lecture videos. Anybody go to review session for the last test? Did it help? Yeah, see? Thanks, Kristen and Javier. Be nice to your TAs. They're super helpful and wonderful. Are you feeling better, Kristen? Excellent.
My bad, it was probably me who gave it to you.
No, I don't think so. I just, like, I don't know, I guess I'm really doctor because my ear hurts.
Oh, really?
Yeah. I have an ear infection.
I hate those.
I used to get when I was a kid all the time. It's been a while. But I was like, sitting
All right, so you think you got everything? You're not sure, maybe? Okay. All right, so somebody tell me what they think the summary should be in sentences. Do it in words. I can sit here forever. I have tea. I have still riding high on cold medicine. I have infinite patience. Yes?
Children who read a story with their name in it read for a significantly longer period of time than children who read a story without their name.
Okay. I love that in every regard but one. Anybody know what the one thing is I might want to fix? Brent?
You said children twice, and it makes it seem like between groups or something.
Yes. That would be a marvelous description of what we did yesterday, but I would like to modify it so that you only refer to the children one time to make it clear that it's the same group of children. Could you do that?
Yeah.
Okay. Anybody want to help her?
So, children who read a story with their name in it read longer than...
Or children will read a story longer when it has their name in it than when it doesn't have their name in it. Does that make sense?
Yeah.
Do you see how it's different?
Yeah.
Okay, so it's a pretty nuanced bit of explanation, but it's important because someone who doesn't know what the researcher did needs to be clear from your description, right? Yes?
So children, the way I said it.
Okay, that's fine.
Children who read their stories with their name on it read longer than children that did not have their name on it.
Well, that's the same problem that she had the first time, which is if you're taught, so maybe this is a rule that we can kind of work on, that when you are talking about a between subject study, it's helpful to refer to the subjects twice because there's two groups. But when you're talking about a within group study, you only want to refer to them one time and then use a pronoun. Like, children will read longer when they read a story with their name in it than when they read a story without their name in it. So we only say the children once. Whereas if I'm doing a between subjects one, I would say children who read a story with their name in it read longer than children who read a story without their name in it. And I say children twice. That helps make it clear that we're talking about two groups compared to one group. Does that help? So I mean, there's not an official rule, but it seems like a good guideline. If you're talking about a between subject study, refer to the two groups separately with a nice clear noun like the participants who did this compared to the participants who did that. And when you're talking about a within subject study, you can say the participants will do this when A differently than when they do B.
So it's always between subject design members two groups. Okay.
Independent groups, yep.
Then within just one.
Right. When there's only one group and you're comparing them to themselves, that's within subjects, yep. Everybody okay with that? So do you see, does that make sense now? Make sense? Okay.
So you don't have to say like significantly longer.
It's better if you say significantly longer. So it would be optimal if you said, children will read for significantly longer when they read a story with their name in it than when they read one that doesn't have their name in it. That would be better. But I'm more concerned with the clear description of whether it's between or within than if you throw that significantly in there. Because I'm assuming that if you say it's longer, the only way that it's longer and it means anything is if it's significant. So that's less of a concern to me than an inaccurate description of the type of design. Okay. So everybody okay with that? Make sense? All right, now we're going to bring that APA-style statistical statement action. Ready? What's the first thing? T. You guys are animals. Animals. Statistics, animals. All right, what's next? Degrees of freedom. So what degrees of freedom do we put here? 5 degrees of freedom of the difference, right? What we use to look up the critical value. Excellent. Okay, equals, what goes next? Positive. That's right, our observed value goes here, right? Our observed value goes here because anybody with the table of critical values can look up the critical value. You just told them what the degrees of freedom was. They look it up themselves. Lazy bums. Have to tell them. What they can't figure out on their own, what they can't figure out on their own is what the observed value is for your data because they don't have all those numbers. Okay? All right, then a comma, and what's next? D, the probability of getting this score given those degrees of freedom is less than 0.05 because that was our alpha. Okay, good. Comma. One-tailed, because it was a one-tailed test, so they need to know that, otherwise they won't be able to look up the critical value and know what the critical value was, because you gotta know that. Okay, and then if we're doing Cohen's d, we would say d equals 1.07, and if we were doing r squared, we would say r squared equals 58%. Done. Dun-dun-dun. Yes.
Dumb question, but what is
No
this?
questions are dumb unless the answer's in the syllabus.
What is this called again? Like this?
This is the APA style statistical statement.
Okay. Alright, I just want to know, like, when I would use this in code, like, if you ask for on the test, like,
On the test, I will have questions that look remarkably like, summarize your results in one or more complete sentences, including an APA style statistical statement.
okay.
Like, it will literally look just like that.
Okay.
So you need to give me the words, and then a comma, and then that.
Okay.
No tricks. I don't need to trick you. It's hard enough already. All right. So is everybody okay with that? Question?
Is it going to say within a problem, or are you going to tell us whether you want Cohen's d or r squared?
Yes, I will tell you which one I want you to do.
Okay, but is there a specific reason why you would choose one over the other?
No. It just depends on which one you like. I will arbitrarily pick one and make you do it, and you won't know which one it is until you get your test. Yes?
Somebody said on the exam, include Cohen's d. So in EPA, that's the only thing you would write, not including the R squared.
Right. If I ask you to calculate Cohen's d, then that's the one you put in your statement. If I ask you to calculate r squared, that's the one you put in your statement. I'm just making sure everybody knows how to do both, because you don't know which one I'm going to ask you to do. So on the test, I could ask you to do an independent groups t-test or a related groups t-test. I could ask you to calculate Cohen's d or r squared. So there's just like all different kinds of options. You don't know what I'm going to ask you to do. Testing is sampling, which means I can pick the population of things I've taught you and pick a random subset, and you have to know it all. All right. So everybody's cool with that. You guys appreciate that you just learned how to do 2 different statistics in 2 days, and you're not panicking.
Yeah.
It's a good thing. All right, now you have to practice. Practice and practice and practice. There's lots of different ways to practice this stuff, okay? First of all, if you go to the website for our class, you'll see that there's a folder up there called More Practice. And under there, there's this handout and links to websites that have practice problems for independent groups and related groups where you can just take the data, plug it into the steps that we've been doing, and figure it out. This particular handout, the review handout, which I'm not going to print out for everybody because I figure if you want it, you can do it. It's not to turn in, it's for your benefit, so your paper and your ink. It goes through step by step what you need to be able to do on this test. So, what I encourage you to do at this point is think about your note card. It's not too early to start preparing your note card for this test. Based on what we did last time and this time, you should have an idea now of what formulas you need and the order in which you need to apply those formulas to solve these kinds of problems. Write those formulas out, and then try doing the problem set or some of these practice problems with what you've written down. And if you realize you don't have enough information, that's something you might want to put on your card. So by trying to plan a little bit and practice and plan and practice and plan, by the time you get done, you should be able to do a whole problem or the whole problem set just using your note card without having to look anything else up. So this review goes through and it says, so you have to be able to tell me first whether the comparison being made is between subjects or within subjects. So you're going to read the problem on the test, and I'm not going to tell you which one it is. You're going to have to decide. Now, part of that's going to be in the wording of the problem. Part of that's going to be, there's going to be clues in the notations I give you, right? If you see calculate S2 little p. Don't go calculating different scores. There's no D. Calculate pooled scores because there's a P. Okay? It's not a trick. If you see S2D, don't go calculating pooled scores. There's no P. It's a D. I know they sound alike, but don't do it. Okay? So just be smart. Pay attention to the clues. Then you have to be able to provide the null hypothesis. You have to be able to provide the alternative hypothesis, right? Just what we've been doing. Okay? Identify whether it's appropriate to do a one-tailed test or a two-tailed test. You guys know how to figure that out, right? Determine the correct value of T critical given whether you're doing a one-tailed test or two-tailed test and what the alpha is. If otherwise unspecified, it's 0.05. Remember, use degrees of freedom pooled if it's independent groups, degrees of freedom difference if it's related groups. Evaluate the null hypothesis, calculate the size of the treatment effect, making sure you know how the formulas are different for the two types of tests, summarize the results in complete sentences, summarize the results in APA style. Okay, those are things you should be able to do for either test. Is everybody okay with that? You're like, okay, I think we covered that, I think I know that. Or I know where to find it in my notes. Okay. May not have it memorized yet, but at least you have a clue. You're like, okay, that sounds vaguely familiar. Then, for independent samples t-tests, I remind you which statistics you need to do. For related samples t-tests, I remind you which statistics you need to do. And then, there are practice problems. So just take a look at this one. Let's see if you can tell which kind of test you should do. In a study of jury behavior, two samples of participants, jury 1 and jury 2. Stop. Which kind of test should you do? Thank you. If you have to get any further into that problem and you don't know yet, you're missing something. Because as soon as it says two samples, you're talking about independent groups. They were provided details about a trial in which the defendant was obviously guilty. Jury 2 was told that some evidence had been withheld from the jury by the judge. Later, participants were asked to recommend a jail sentence. And then it says, so now you know you're doing the independent groups t-test. So if you can't remember the order of things you need to do, grab your independent groups worksheet. Right there. And go through the steps. Just crank through the steps. The TAs have the keys. You will not get them. The only way to find out the answers to these problems is to talk to the TAs, which means you need to have them done before you go to study group. You can't go to study group and say, tell me the answer to the practice problems. You have to try yourself first. Because they will not tell you what the answers are unless you have tried. Because that doesn't help you. Okay. Let's try another one. Numerous studies have found that males report higher self-esteem than females, especially for adolescents. The results below are typical for studies of this type. Given alpha 0.05, determine whether or not these data support this claim. Use R-squared to calculate the size of the treatment effect. Oh look, males and females. Between subjects or within subjects? Between. Two different groups, right? Independent groups. The males and the females are two different groups of students. Stevens, Atkins, and Kingston conducted an experiment comparing swearing to other responses to pain. Yes, swearing for science. In the study, participants were asked to place one hand in icy cold water for as long as they could bear the pain. Half the participants were told to repeat their favorite swear word over and over for as long as their hands were in the water. The other half repeated a neutral word. The researchers asked the participants to rate their pain on a scale from 1 to 10. After a brief rest, the two groups switched words and repeated the ice water plunge. Thus, all participants participants experienced both conditions, swearing and neutral, with half swearing on their first plunge and half swearing on their second plunge. All right, what do you know about this study? It's within subjects because everybody did everything. They just counterbalanced it. Okay. So there you have one group of participants with swearing scores and neutral scores. Yes?
So, is there an example of like a two-tailed test, or when you would use a negative critical value or observe?
Maybe. I don't know, I'll remember off the top of my head.
I think the first one is two-tailed.
The first one is two-tailed, because yeah, we just say, determine whether the difference in information provided to the two juries resulted in a different length of recommended sentence. So that would be a two-tailed test, because we're just saying, was there any difference? We're not predicting what the direction of the difference would be. Because it's possible that thinking that information had been withheld would make you recommend a longer sentence, because you might think it was something that would prejudice the jury, or you might think that it was going to have them give a shorter sentence because information that would make the person less guilty was being withheld by an unethical judge. So it depends on how you think judges behave. So who knows how to determine. So yeah, that's two difference. I typically try to mix it up on practice problems, but I don't remember exactly which one. Okay. So then we have research results indicate that physically attractive people are also perceived as being more intelligent. I suffer from this all the time. As a demonstration of this phenomenon, a researcher obtained a set of 10 photographs, 5 showing men who were judged to be attractive and 5 showing men who were judged to be unattractive. The photographs were shown to a sample of 25 college students who were asked to rate the intelligence of the person in each photo on a scale of 1 to 10. For each student, the researcher determined the average rating for the attractive and unattractive photos. She then computed the difference in the two scores. Well, there you go. In general, the participants rated the attractive men as more intelligent than the unattractive men. Oh, look, there's a mean of the difference and a standard deviation of the difference. What kind of test are you doing? Related groups, right? This is within subjects. See, it's not so bad. You can do it. An elementary school teacher wants to investigate the influence of background noise on classroom performance for children aged 10 to 12. He has one class listen to calming music each day while working on arithmetic problems. A second class completes the same problems in a room with no music. The teacher records the student's accuracy for solving the problems with the results below. Between subjects or within? Between two different groups of kids, right? When you get a surprisingly low price on a product, do you assume that you got a really good deal or that you bought a low quality product? Research by Yan and Sengupta suggests that you are more likely to associate low price and low quality if someone else makes the purchase, but not if you purchase it yourself. So if other people buy cheap stuff, it's because they bought crap, but if you buy cheap stuff, it's because you're wise and a good spender. Isn't that nice? Human beings are so nice that way. Okay. In an attempt to replicate these findings, a Georgia State student asked 16 college students to rate the quality of low-priced items purchased by a friend or purchased by the participant. On average, self-purchases were rated of higher quality. Determine whether these values are consistent with Yan and Sengupta's results. Okay? Between and within. Within, because the person rates both ones that they purchased and ones that someone else purchased. Right? So they're getting ratings from the same people. And plus there's that mean of the difference, sum of squares of the difference. Okay? All right, folks. Your job now is to work on those things. You have practice problem. We've got problem set number 2 up there. Okay? You want to start working on problem set number 2? Lots of different kinds of problems. Again, not telling you which kind of test you're supposed to do. Just get up there and do it. Okay. There is one thing. Oh, I'm looking at here. I realize there's one thing I need to tell you that I haven't told you yet, so you can't go. Plus, we have 15 minutes, so what are you in a hurry for anything? Let's jump over here to independent groups for a second. Let's come back over here to independent groups. Now, remember we talked about last time, we were first talking about between subject designs, that the most important thing when you're designing a between subject study is creating groups that are similar enough to compare, right? That's your number one challenge. Because you've got these issues with individual differences, right? Well, we actually have a statistic that we can use to tell whether the groups are similar enough to compare. And that statistic is called Fmax. Now, if you look at the handout, if you were reading it carefully when we were going over this problem last time, you saw down here at the bottom a note that says once you have calculated the sample variance for group 1 and the sample variance for group 2 and something called DF common, which I'll tell you what that is in a second, it's possible to perform an Fmax test to verify that the samples being compared display homogeneity of variance. Well, homogeneity. Homogeneity has that homo prefix, right? That's same, right? Homogeneity of variance is the statistical value for being similar enough to compare. That the variance of the two groups is close enough that we feel like we can compare them and the outcome will be statistically meaningful. So I want to talk to you now about how we do that so that you will be able to answer this one last question on the problem set and be able to do this kind of problem on the test. Now this only happens with independent groups t-tests, right? We only do this for independent groups. It's the only time we have two groups that need to be similar enough to compare, right? Okay. So Fmax is pretty straightforward. In order to calculate Fmax, you need to have the sample variance for group 1 and the sample variance for group 2. Okay. You need to know the sample variance for group 1 and the sample variance for group 2, okay, for a t-test. If we look back at our notes from last time, what was the sample variance for group 1? That's the sample variance for the modified story.
18.67.
I don't know. I'm asking you. 18.67 is the vote. Okay. 18.67. And what was the sample variance for the ordinary story group from last time? 5.6. So that's our sample variance for the two separate samples. Okay. Now, if I want to calculate Fmax observed, the observed value, here's what I do. I'm going to take the larger sample variance, and I'm going to divide it by the smallest sample variance. That's literally the formula. The larger sample variance divided by the smaller sample variance. So it's a ratio. So that means I'm going to take 18.67 and divide it by 5.6. What is that value? 3.33? Yep. Okay. That's my F observed. Fmax observed. Now, if you take your packet of critical value tables, go to page 2. You will see you have critical values for the Fmax statistic. So what do we need to know to look up a critical value for Fmax? We need to know n minus 1. That sounds like degrees of freedom of some kind. We have to know k, which is the number of samples. And we have to know alpha. If we're looking at 0.05, we look in light phase type. Those are the ones on the top. If we look at alpha 0.01, we look at bold face type, those are the ones underneath. Okay? Now, anytime we do a t-test, anytime we're doing an independent groups or related groups t-test, well, it doesn't matter for related groups, we say we have two samples, kind of, because we've got two groups, kind of. For the independent groups t-test, we definitely have two samples, right? We have the sample, in this case, that read the modified story, and the sample that read the ordinary story, right? So in this case, K is 2. So we're looking here, okay? Now we have to figure out this n minus 1 thing. This n is talking about the n common. And n common means it's the number that the samples have in common. The only way you can do Fmax is if both of your samples are the same size. They have to be the same size. Well, and we can do Fmax with more than two groups too. So as long as all the samples are the same size, you're fine. So in this case, what is the n that our samples have in common? 6, right? Both of our samples are of size 6. So that's the n we're talking about. So now I need to figure out degrees of freedom common, which is n common minus 1. It's really tricky. 6 minus 1. 5. I know, the math here, it's overwhelming. So we're going to go look on this chart now. Under degrees of freedom 5, knowing that alpha is 0.05, because we use the same alpha for Fmax as we use for our t-test. And it says here that the critical value is 7.15. Right? Okay. So now we have to evaluate the null hypothesis. And it goes like this. What does that tell you? Now, is that a good thing or a bad thing? In this case, it's a great thing. And here's why it's a great thing. What we just retained the null hypothesis. What does that mean? It means there is no difference between our groups. And that's what we want, because that's what homogeneity of variance means. That the variances are effectively the same. So we want, in the case of Fmax, to retain the null hypothesis when we do this comparison. If we do, that means that we have groups that are homogeneous enough to compare statistically, and the rest of the test makes sense. If you're ever looking at independent groups data, and you calculate Fmax and reject the null hypothesis, stop. Because there's absolutely no point in your going on. Your groups are already so different. The individual differences between the groups are so extreme that you're going to probably commit a type 1 error. You're going to get a statistical difference between those groups no matter what you do. And it may or may not have anything to do with your hypothesis or your manipulation. Yes?
What if we accidentally put filters on? Because basically it's the same thing, right? Instead of rejecting.
I'll always ask you, do we reject or retain?
Reject.
I will always say, when it comes to evaluate the null hypothesis, it literally will say, evaluate the null hypothesis, circle 1. Reject or retain. We either reject the null, because I think failing to reject the null is confusing.
It is.
And I'm like, it's confusing enough. Why do we have to use confusing words? So we either reject the null or we retain the null. That's how that's my strategy. I figured we should make it easier wherever we can. Because there's enough stuff that's challenging. So on the problem set, it asks you, why would a researcher perform an Fmax test prior to performing a t-test on 2 independent samples? Well, because they need to make sure that the samples are similar enough to compare. Because if the samples are already too different, performing the t-test will probably just result in a type 1 error. That's not good. Why do we never do it for a t-test on related groups? Because you don't need to. They already have homogeneity of variance. It's the same people. Done. Okay, so don't get all worried and stuff about that question. It's pretty straightforward. Yes?
Will we do everything on the test?
If you get the independent groups t-test, you will. Yes, if you get the independent groups t-test, there is entirely a chance you will be asked to do Fmax. So you should know how to do it too. But it's not very hard. And if you followed all the steps, you will have everything you need. And on the test, I will say, if I want you to do Fmax, I'll ask you, calculate the sample variance for this sample, calculate the sample variance for that sample, calculate Fmax observed, look up your critical value, evaluate the null hypothesis, tell me whether they have homogeneity of variance. So literally, if you just know the steps to calculate that, you're good. I have not solved this problem, here's a giant blank piece of paper, just fill in all the steps. Because then the answers are all over everywhere and it's really hard to grade. I want everything in exactly the place where I want it. So it's really easy for me to find. Okay. You should know everything you need to know to do the problem set. You should know everything you need to know to read and understand the article.